Welcome. Today, we're diving deep into the 6L80 transmission and its Transmission Electro-Hydraulic Control Module, or TEHCM. We'll explore the critical differences between TEHCM versions and identify their most common failure points. The 6L80 is a 6-speed automatic transmission widely used in GM vehicles. This complex electro-hydraulic system relies heavily on precise electronic control for its operation. At the heart of this transmission's control system is the TEHCM, the Transmission Electro-Hydraulic Control Module. This critical component houses the transmission control module and manages all hydraulic functions through electrical signals. Here's where it gets complex. Different versions of the TEHCM exist for the same 6L80 transmission. These variations have different part numbers and limited interchangeability, making proper identification crucial for repair success. Understanding TEHCM failures is equally important. These units are prone to several specific failure modes that can cause a wide range of transmission problems, from harsh shifts to complete loss of movement. Throughout this series, we'll examine each of these failure modes in detail, explore the differences between TEHCM versions, and provide you with the knowledge needed for effective diagnosis and repair. Understanding these nuances is crucial for anyone working with 6L80 transmissions. The TEHCM is a critical component that serves as the brain of the 6L80 transmission system. Understanding what it is and why it matters is essential for anyone working with these transmissions. TEHCM stands for Transmission Electro-Hydraulic Control Module. Each letter represents a key aspect of this sophisticated component. Think of the TEHCM as the brain of the transmission. Just like a computer processor controls data flow and operations, the TEHCM manages all the transmission's electronic and hydraulic functions. Now let's look at what the TEHCM actually contains and how it's structured. The TEHCM houses the Transmission Control Module, or TCM. This physical unit features a silver-finned casing for heat dissipation and a black electrical connector. Inside, it contains sophisticated microprocessors and circuits. The TEHCM controls various solenoids and sensors throughout the transmission. Let's examine the solenoid layout. This diagram shows the solenoid layout within the TEHCM. It controls shift solenoids for gear changes, pressure control solenoids for hydraulic pressure, transmission fluid pressure switches, and the temperature sensor. The TEHCM also interfaces with the valve body, which contains additional solenoids and control valves. The valve body contains additional solenoids, including the torque converter clutch solenoid, PWM solenoid, and various shift solenoids. All of these work together under TEHCM control. Now let's understand why the TEHCM is so critically important to transmission operation. The TEHCM is critical because it converts electrical signals into hydraulic actions. It controls all gear shifts, manages hydraulic pressure, and monitors vital transmission parameters. Most importantly, without a functioning TEHCM, the transmission will not shift correctly, if at all. This makes it one of the most critical components in the entire transmission system. In summary, the TEHCM serves as the intelligent control center that bridges electrical commands with hydraulic actions, making modern transmission operation possible. Traditional hydraulic transmissions use mechanical pumps and valves to control fluid pressure and flow. The system relies on purely mechanical components to manage gear changes. The 6L80 uses electro-hydraulic control, where electronic control modules send precise electrical signals to solenoids. These solenoids then convert the electronic commands into hydraulic pressure and flow control. Let's examine the actual solenoid layout in the 6L80 transmission. This technical diagram shows the complex arrangement of solenoids and switches that control transmission operation. Each solenoid in this assembly has a specific function. Pressure control solenoids regulate hydraulic pressure, while shift solenoids control gear changes. The electronic control module coordinates all these components. Solenoids control the application of clutch packs within the transmission. When the control module sends a signal, the solenoid opens or closes, directing hydraulic pressure to engage or disengage specific clutch sets. The solenoids also control the torque converter lockup system. Let's examine the torque converter assembly and understand how electronic control manages this critical component. This electro-hydraulic control provides exceptional precision in timing and pressure control. However, it also introduces more potential failure points compared to purely hydraulic systems, as both electronic and hydraulic components can fail. Understanding electro-hydraulic control is essential for diagnosing 6L80 transmission issues. The complexity of this system requires specialized knowledge of both electronic and hydraulic principles for effective troubleshooting. The 6L80 transmission features sophisticated adaptive learning capabilities. The transmission control module continuously monitors and adjusts shift parameters based on your driving habits and component wear patterns. The TEHCM constantly monitors multiple parameters, including vehicle speed, engine load, transmission temperature, and component wear. This data feeds into adaptive algorithms that optimize shift timing and pressure. Different driving patterns create different adaptation strategies. Gentle, consistent driving results in smooth, fuel-efficient shift patterns. Aggressive driving causes the TEHCM to adapt with firmer, quicker shifts to handle the increased demands. The TEHCM adapts multiple parameters over time. Shift timing becomes more precise, line pressure adjusts for wear compensation, clutch apply rates optimize for smoothness or performance, and torque converter lockup points adapt for efficiency. Resetting adaptations can temporarily improve shifting issues by returning all learned parameters to factory defaults. This often results in more consistent shift quality initially, as shown by these shift quality measurements. However, it's crucial to understand that resetting adaptations is only a band-aid solution. If there are underlying mechanical problems like worn clutches, valve body issues, or solenoid failures, the symptoms will return as the TEHCM relearns the faulty conditions. The key takeaway is that proper diagnosis of mechanical issues must come first. Adaptation resets should only be performed after confirming that the transmission's hardware is functioning correctly, or as a diagnostic tool to temporarily isolate software versus hardware problems. Understanding TEHCM manufacturing and interchangeability is crucial for proper diagnosis and replacement. All 6L80 TEHCMs are manufactured by Bosch specifically for General Motors. However, this manufacturing relationship creates an important complexity. Different 6L80 applications require TEHCMs with different part numbers, and these units are typically not interchangeable between applications. The critical point to understand is that these TEHCMs are application-specific. A TEHCM designed for a Corvette cannot simply be installed in a Silverado, even though both use the 6L80 transmission. This interchangeability issue has significant implications when sourcing replacement TEHCMs. Technicians must ensure they obtain the exact part number specified for their particular vehicle application to avoid compatibility problems. Remember, while all 6L80EMs share the same Bosch manufacturing quality and basic design principles, their specific calibrations and configurations make them unique to each application. This specificity is what ensures optimal transmission performance in each vehicle. Despite the limited interchangeability between different TEHCM units, there's a fascinating commonality that connects them all. Every TEHCM uses the exact same microprocessor design. This shared microprocessor serves as the brain of the TEHCM, containing all the essential components needed for processing transmission control signals across multiple GM transmission families. The transmission families that share this common microprocessor include the 6L45, 6L50, 6L80, 6L90, and 6T70. Each represents different applications and torque capacities, yet they all rely on the same fundamental processing architecture. This common design foundation means that a microprocessor failure in one TEHCM type could potentially manifest similar symptoms across all these transmission families, making diagnostic patterns more predictable. The implications of this shared architecture are significant for technicians and engineers. Understanding that the same microprocessor controls different transmission types helps explain why certain failure modes and diagnostic codes appear consistently across the entire GM transmission family. This standardization also means that improvements or updates to the microprocessor design can benefit multiple transmission platforms simultaneously. while any discovered vulnerabilities may affect the entire range of applications. The software and calibration differences in 6L80 TEHCMs create important compatibility considerations that technicians must understand for successful repairs and replacements. The transmission control module communicates with the engine control module using a sophisticated dual-strand CAN bus network. This high-speed digital communication system allows real-time data exchange between these critical control units. Each control module contains sophisticated internal components including microprocessors, memory storage, and communication interfaces. The EEPROM stores the specific software calibration, while the ROM contains the operating system that varies by model year. TEHCM compatibility follows specific year groupings. Units from 2006.5 through 2009 are generally interchangeable within that range. Similarly, 2010 through 2013 units work within their group. However, crossing between these year groups requires reprogramming. Each model year incorporates unique operating system features, including different shift strategies, updated diagnostic protocols, modified pressure control algorithms, and enhanced adaptive learning parameters. These differences prevent direct compatibility between year groups. The solution for cross-year compatibility is reprogramming the TCM with the correct software for the target vehicle. This process updates the operating system and calibration parameters to match the specific model year requirements, ensuring proper communication and operation. Understanding these software and calibration differences is crucial for successful TEHCM replacement and repair, preventing compatibility issues that could lead to transmission malfunctions. Capacitor failure represents one of the most critical vulnerabilities in certain 6L80 TEHCMs. This failure can cascade into serious microprocessor malfunctions and widespread transmission problems. TEHCMs manufactured during a specific 54-day window from July 28 to September 19, 2017 are particularly susceptible to capacitor failure. This represents a critical manufacturing defect that affects thousands of units. The affected units can be identified by their build date codes, 7209 and 7262. These codes represent specific weeks during the problematic manufacturing period when defective capacitors were installed. This image shows a typical failed capacitor from an affected TEHCM. Notice the physical damage, including holes in the casing and frayed edges. These failures result in electrolyte leakage and complete loss of voltage regulation capability. When the capacitor fails, it creates a cascade effect. The failed capacitor disrupts power regulation to the microprocessor, causing it to malfunction. This microprocessor failure then leads to complete loss of transmission control and a range of serious symptoms. The capacitor is integrated deep within the TEHCM's electronic circuitry, making field repair impossible. When capacitor failure occurs in units with build dates 7209 or 7262, complete TEHCM replacement is the only solution. This critical vulnerability highlights the importance of checking build dates before installation. Solenoid malfunctions are among the most common failures in the 6L80 transmission system. Understanding their symptoms and causes is crucial for proper diagnosis and repair. Solenoids in the 6L80 transmission are electromagnetic valves that control hydraulic pressure throughout the system. They manage gear shifts, regulate torque converter lockup, and provide precise timing control for optimal transmission operation. Solenoid failures typically fall into two categories: electrical and mechanical. Electrical failures include open circuits, short circuits, and high-resistance connections. Mechanical failures involve stuck valves, worn seals, and debris contamination that prevents proper operation. Solenoid malfunctions manifest in several distinct ways. Harsh shifts occur when solenoids fail to modulate pressure smoothly. Slipping happens when solenoids cannot maintain proper clutch engagement. Incorrect gear selection results from faulty shift solenoids not responding to control signals. Several factors contribute to solenoid failure. Heat damage from high fluid temperatures can destroy internal components. Contamination from metal particles and dirty fluid can cause valves to stick. Normal wear over time and high mileage leads to seal deterioration. Electrical issues like low voltage and poor connections prevent proper solenoid operation. Proper diagnosis of solenoid malfunctions requires specialized testing equipment. Oscilloscopes analyze solenoid waveforms, measure duty cycles, and test response times. Multimeters verify resistance values, check voltage supply, and perform continuity testing. Without proper diagnostic tools, solenoid problems can be misdiagnosed, leading to unnecessary repairs. Pressure switches are critical components within the TEHCM that monitor hydraulic pressure levels throughout the transmission. When these switches fail, they can cause significant operational problems. Pressure switches work by monitoring hydraulic pressure levels within the transmission. When pressure reaches a specific threshold, typically around 100 psi, the switch activates and sends a signal to the transmission control module. The pressure switch contains several critical components, including a pressure-receiving diaphragm, range spring, micro-switch contacts, and most importantly, sealing films that prevent hydraulic fluid leakage. When switch films become damaged, they allow hydraulic fluid to leak internally. This creates inaccurate pressure readings and leads to delayed forward or reverse engagement as the transmission struggles to build proper pressure. The primary symptoms of pressure switch failure include delayed forward and reverse engagement, inconsistent shift timing, and pressure-related diagnostic trouble codes. These symptoms often worsen over time as the damage progresses. During troubleshooting, it is crucial to inspect pressure switches for damaged films, fluid contamination, and proper electrical connections. A systematic inspection can identify switch-related issues before they cause more extensive transmission damage. Remember that early detection of pressure switch issues can prevent more costly transmission damage. Regular inspection and proper diagnosis of these components is essential for maintaining transmission reliability. Valve body contamination is one of the most common causes of TEHCM failures in the 6L80 transmission. Metal debris and particles can cause critical valves to stick, leading to serious operational problems. In a clean valve body, valves move smoothly within their channels. The hydraulic fluid flows freely, allowing precise pressure control and smooth shifting operations. However, when metal contamination and debris accumulate in the valve body, these particles interfere with valve movement. The debris acts like sand in a precision mechanism, causing valves to stick and bind. This valve body diagram shows the intricate network of channels and valves that control hydraulic pressure. When contamination occurs, it affects multiple aspects of transmission operation, including pressure regulation and shift quality. Sticking valves severely impact pressure regulation. Normal operation maintains steady hydraulic pressure, but contaminated valves cause erratic pressure fluctuations that lead to poor transmission performance. The most effective prevention against valve body contamination is regular transmission fluid changes. Fresh fluid removes accumulated debris and metal particles, maintaining the clean environment that valves need to operate properly. Remember, valve body contamination is preventable through proper maintenance. Regular fluid changes are essential for keeping your 6L80 transmission operating smoothly and avoiding expensive TEHCM failures. Static discharge poses a serious threat to TEHCM components during shipping and handling. Understanding how to prevent electrostatic discharge damage is crucial for protecting these sensitive electronic modules. Static electricity naturally builds up on the human body through everyday friction with clothing, carpets, and other surfaces. This charge accumulation can reach thousands of volts without us even noticing. The TEHCM contains highly sensitive electronic components that can be permanently damaged by static discharge. Even a small spark that you cannot see or feel can destroy delicate circuits inside the module. When a charged hand or tool approaches the TEHCM connector, static discharge can jump across the gap. This invisible damage can cause immediate failure or create weak points that fail later under normal operation. Proper anti-static protection is essential when handling TEHCMs. Always use an anti-static wrist strap connected to a good ground, handle components by their edges, and never touch the connector pins directly. Following these best practices will significantly reduce the risk of static discharge damage to TEHCM components. Remember that prevention is always better than replacement when dealing with these expensive and sensitive electronic modules. When a TEHCM begins to fail, it produces specific symptoms that technicians must recognize quickly. Early detection of these warning signs can prevent catastrophic transmission damage and costly repairs. The first and most common symptom is the illumination of the malfunction indicator lamp, or check engine light. This warning light appears when the transmission control module detects specific diagnostic trouble codes. A complete loss of forward or reverse movement indicates severe TEHCM failure. The transmission control module can no longer command the necessary solenoids to engage the appropriate clutch packs. Harsh or delayed shifts occur when solenoids within the TEHCM begin to malfunction. These solenoids control hydraulic pressure to the clutch packs, and when they fail, shift quality deteriorates significantly. Stalling or hesitation during acceleration indicates the TEHCM cannot properly control torque converter lockup or gear selection. This creates dangerous driving conditions and poor vehicle performance. When the TEHCM fails completely, the transmission enters a default or limp mode, typically staying in second or third gear. This safety feature prevents further damage but severely limits vehicle operation. Shudder and vibration symptoms often indicate torque converter clutch problems controlled by the TEHCM. These vibrations are most noticeable during lockup engagement and can be analyzed using specialized diagnostic equipment. These 6 primary symptoms, MIL illumination, loss of movement, poor shift quality, performance issues, default gear operation, and vibration, provide clear indicators of TEHCM failure. Recognizing these symptoms early allows for proper diagnosis and prevents further transmission damage. Remanufacturing TEHCMs has become a common practice in the automotive industry, but the quality can vary significantly between different suppliers. The remanufacturing process involves disassembling used CMs, cleaning components, replacing worn parts, and reassembling them. This practice is popular because it can save 40 to 60% compared to new units. However, quality inconsistency is a major concern with remanufactured TEHCMs. Common problems include inadequate cleaning, reuse of worn components, poor quality control, incorrect assembly torque, and missing software updates. The difference between good and poor remanufacturing is significant. Reputable remanufacturers use ultrasonic cleaning, install new seals and gaskets, perform comprehensive testing, verify software, and provide quality certification. In contrast, poor quality remanufacturers may only perform basic cleaning, reuse worn components, conduct limited testing, skip software updates, and offer no quality guarantees. Reputable remanufacturers follow structured quality management processes, similar to this diagram. Each step from inventory through final inspection ensures consistent quality and reliability. When choosing a remanufacturer, research their reputation, verify warranty terms, ask about testing procedures, confirm they update software, check for certifications, and be wary of extremely low prices, which often indicate poor quality. Remember, a failed remanufactured TEHCM can cause more damage than the original problem, making it crucial to choose quality over the lowest price. When standard remanufactured TEHCMs prove unreliable, Sonax offers a premium alternative with their rigorous remanufacturing process. Sonax is a well-established company in the transmission industry, known for their high-quality remanufactured components and innovative solutions. The Sonax remanufacturing process begins with ultrasonic cleaning, a sophisticated method that uses high-frequency sound waves to remove contaminants at the microscopic level. After ultrasonic cleaning, each TEHCM undergoes rigorous inspection and testing to ensure all components meet strict quality standards before reassembly. Sonax remanufactured TEHCMs include brand new pressure switches and filter plates, replacing components that commonly fail in original units. Critical to remember: all Sonax remanufactured TEHCMs must be reprogrammed after installation to ensure proper communication with the vehicle's engine control module and optimal performance. Sonax remanufactured TEHCMs represent a premium solution for 6L80 transmission repairs, offering superior quality control and reliability compared to standard remanufactured units. When valve body wear becomes a problem in the 6L80 transmission, aftermarket solutions provide cost-effective repair options that can restore proper function without requiring complete transmission replacement. Valve body wear manifests as scoring and contamination damage that causes valves to stick. This leads to poor pressure regulation and degraded shift quality, requiring intervention to restore proper transmission operation. The pressure regulator valve is particularly susceptible to wear. Critical components like the control spring, diaphragm assembly, valve bore surfaces, and orifice passages can all be affected by contamination and normal wear over time. Aftermarket kits provide comprehensive solutions for valve body wear. These kits include new valve components, precision machined parts, improved materials, and installation hardware needed for proper repair. The benefits of using aftermarket solutions include restored pressure regulation, improved shift quality, cost-effective repair compared to transmission replacement, and extended service life for the transmission system. When installing aftermarket valve body repair kits, proper installation is crucial. Professional installation is recommended, along with correct torque specifications, clean assembly environment, system flush, and adaptive learning reset to ensure optimal performance. Aftermarket kits represent a practical and cost-effective approach to addressing valve body wear in 6L80 transmissions, providing the components and materials needed to restore proper pressure regulation and shift quality when installed correctly. Modern automotive transmissions have undergone a dramatic transformation over the past few decades. What were once purely mechanical systems have evolved into sophisticated electro-hydraulic marvels of engineering. Traditional transmissions from the 1980s relied primarily on mechanical and basic hydraulic controls. These systems had relatively few electronic components and were simpler to diagnose and repair. In contrast, modern transmissions like the 6L80 incorporate over 50 different electronic control elements, including multiple solenoids, pressure sensors, temperature monitors, and sophisticated control modules. This complexity is clearly visible when we examine the physical components of a modern transmission system. Here we can see a modern transmission with its associated wiring harness. Notice the complexity of the electrical connections required to operate the various solenoids, sensors, and control modules. The internal complexity becomes even more apparent when we examine a detailed cutaway view of the transmission. This cutaway reveals the intricate integration of electronic and hydraulic systems. The TEHCM must coordinate with multiple solenoids, pressure sensors, and adaptive control algorithms to manage gear changes and torque converter operation. This increasing complexity has profound implications for automotive technicians and repair facilities. Today's transmission technicians must possess a much broader skill set than their predecessors. They need training in electronic diagnostics, software programming, advanced scan tool operation, and must stay current with rapidly evolving technology. The diagnostic process itself has become exponentially more complex. Where once a technician might check fluid levels and perform basic pressure tests, modern diagnosis requires sophisticated electronic analysis. This complexity trend has significant implications for the automotive industry. Repair costs have increased due to the sophisticated nature of modern transmissions. Diagnostic procedures take longer, and shops must invest in specialized equipment and ongoing technician training to remain competitive. Understanding this complexity is crucial for anyone working with modern transmissions like the 6L80. The days of simple mechanical repairs are largely behind us, replaced by an era requiring both traditional mechanical skills and advanced electronic expertise. Proper diagnostics are absolutely critical when dealing with 6L80 TEHCM issues. Too many technicians fall into the trap of throwing parts at problems instead of systematically diagnosing the root cause. The financial impact of poor diagnostics is staggering. The wrong approach can cost over $1,400 in unnecessary parts, while proper diagnosis typically costs under $500 total. Modern diagnostic equipment is essential for accurate TEHCM diagnosis. This includes OBD2 scanners, digital multimeters, pressure gauges, oscilloscopes, and specialized transmission software. Electrical testing is fundamental to TEHCM diagnosis. Check battery voltage, ignition circuits, solenoid resistance values, ground integrity, and CAN bus communication before replacing any components. Follow this systematic diagnostic approach. First, read diagnostic trouble codes, then check power and ground circuits, test individual solenoids, verify hydraulic pressures, check software versions, and only then replace components if testing confirms failure. Remember this fundamental principle. Symptoms only point to problems, but proper testing reveals the actual root causes. This systematic approach saves both time and money while ensuring reliable repairs. Software updates and reprogramming have become critical components in modern transmission repair and optimization. As transmissions become more electronically controlled, keeping diagnostic software current is essential for accurate diagnosis and proper repair. The modern diagnostic workflow begins with connecting your diagnostic tool to the vehicle. However, before proceeding with any diagnosis, it's crucial to verify that your diagnostic software is running the latest version available. Professional technicians rely on sophisticated diagnostic equipment to communicate with the transmission control module. These tools require regular software updates to maintain compatibility with the latest vehicle software and to access new diagnostic capabilities. Modern diagnostic software provides comprehensive system monitoring and testing capabilities. Tools like ProScan offer real-time data visualization, allowing technicians to observe transmission behavior under various operating conditions and identify issues that might not trigger diagnostic trouble codes. When a TEHCM requires reprogramming, technicians must follow a precise process. This begins with identifying the correct software version for the specific vehicle and transmission combination, then establishing a secure connection to download and install the updates. After successful installation, it's critical to reset the adaptive learning parameters. This allows the transmission to relearn optimal shift points and pressure settings based on the new software calibration. Maintaining current software versions provides significant benefits for transmission repair shops. Updated diagnostic software improves accuracy by including the latest diagnostic trouble codes and parameters, while updated transmission calibrations enhance performance and reduce the likelihood of customer comebacks. To maximize the benefits of software updates, transmission shops should implement best practices for software management. This includes scheduling regular update checks, maintaining current subscriptions, and ensuring all technicians are trained on proper update procedures. Remember that software updates and reprogramming are not just maintenance tasks, but essential tools for delivering quality transmission repairs. Staying current with software ensures you have access to the latest diagnostic capabilities and calibration improvements that can make the difference between a successful repair and a costly comeback. As new 6L80 TEHCM parts become increasingly difficult to find and expensive to source, the automotive industry is turning toward remanufacturing and remachining as viable alternatives. Several factors are driving this trend. New parts are becoming increasingly scarce as manufacturers focus on newer transmission designs. The rising costs of original equipment manufacturer components make remanufacturing an attractive economic option. The remanufacturing process involves several critical steps that require specialized equipment and expertise. Let's examine the typical workflow for remanufacturing TEHCM components. The process begins with thorough inspection to identify worn or damaged components. This is followed by intensive cleaning using ultrasonic baths and specialized solvents to remove all contaminants. Here we see a complex valve body assembly that would undergo this remanufacturing process. Notice the intricate network of channels, ports, and electronic components that must be carefully restored. Precision machining restores worn surfaces to original specifications, followed by comprehensive testing to ensure proper function and reliability. Remanufacturing requires specialized equipment that represents significant capital investment. Let's examine the key equipment needed for professional remanufacturing operations. Professional remanufacturing facilities require extensive cleaning equipment, including ultrasonic tanks for removing microscopic debris and high-pressure washers for initial cleaning. Precision machining equipment is essential for restoring worn surfaces. CNC milling machines, precision lathes, and surface grinders ensure components meet original specifications. This disassembled valve body shows the complexity of components that must be individually inspected, cleaned, and potentially remachined during the remanufacturing process. Beyond equipment, remanufacturing requires specialized expertise and knowledge that takes years to develop. The human element is crucial for quality remanufacturing. Technicians must understand complex hydraulic systems, electronic component testing, and precision measurement techniques. Quality control procedures ensure each remanufactured component meets strict standards. These precisely machined components represent the end result of professional remanufacturing, parts that meet or exceed original specifications while providing cost-effective alternatives to new components. As the automotive industry continues to evolve, remanufacturing and remachining will play increasingly important roles in maintaining older transmission systems like the 6L80, providing sustainable and economical solutions for component replacement. In this case study, we examine a critical installation error that can cause severe damage to the TEHCM and valve body, using incorrect bolt lengths during assembly. Proper bolt specifications are absolutely critical for TEHCM installation. Each bolt must meet exact length, thread pitch, torque, and material requirements to ensure safe and reliable operation. The valve body assembly contains precisely machined passages and chambers. When bolts are too long, they can penetrate through the valve body, damaging internal passages and creating metal debris. When too short, they provide insufficient clamping force. Thread damage from incorrect bolts creates immediate shifting problems and can lead to catastrophic long-term damage. Even minor thread damage can cause galling and progressive failure of the entire transmission system. Proper installation requires careful attention to bolt specifications, clean preparation, and precise torque application. Always use original equipment or equivalent bolts that meet exact manufacturer specifications to prevent costly damage. Remember, this seemingly simple installation error can result in thousands of dollars in transmission damage. Taking time to verify bolt specifications is always worth the investment. In this case study, we examine how torque converter failure creates a cascade of damage throughout the transmission system, affecting the pump, valve body, and ultimately the TEHCM. The torque converter is a critical component that transfers power from the engine to the transmission using hydraulic fluid. When it fails internally, it generates metal debris that contaminates the entire transmission system. When internal components wear or fail, they create metal particles and debris. This contamination is carried by the transmission fluid throughout the entire hydraulic system. Here we see the contamination path through the transmission. The debris flows from the torque converter through the pump, into the valve body, and eventually reaches the TEHCM components. This is what actual contamination looks like inside a transmission. The black debris you see here is the result of torque converter failure, coating all internal components and clogging critical passages. The valve body and TEHCM are particularly vulnerable to this contamination. The debris clogs solenoid screens, damages pressure switches, and causes valves to stick in their bores. This detailed valve body diagram shows the critical filter screens and passages that become clogged with debris. Notice the PWM solenoid filter screen highlighted in green. This is often the first component to fail when contamination occurs. The key to preventing this cascade of damage is early detection and prompt action. When torque converter issues are identified, immediate replacement prevents contamination from spreading throughout the transmission system. Remember, torque converter failure is not just a single component issue. It creates a domino effect that can destroy the entire transmission system if not addressed promptly. Early intervention saves both time and money. As we conclude our comprehensive examination of 6L80 TEHCM variations and failures, it's important to understand the key takeaways that will help you work effectively with these complex transmission control systems. The 6L80 TEHCM represents a sophisticated electro-hydraulic control system with multiple interconnected components. This exploded view shows the transmission's complexity. with the TEHCM serving as the brain that coordinates all these mechanical and hydraulic elements. Throughout our series, we've identified 4 critical failure points in 6L80 TEHCMs: capacitor failures in specific build date ranges, solenoid malfunctions causing shift issues, pressure switch problems leading to engagement delays, and valve body contamination resulting in sticking valves. Proper diagnostic procedures are absolutely critical when working with 6L80 TEHCMs. The complex wiring and electronic systems require systematic testing to avoid costly misdiagnosis and unnecessary component replacements. Regular maintenance and quality repair solutions can significantly extend 6L80 transmission life. Companies like Sonax offer thoroughly tested, remanufactured TMs and aftermarket solutions that address known failure points with improved designs. In conclusion, the 6L80 TEHCM may be complex, but with proper understanding of its failure patterns, quality diagnostic procedures, and regular maintenance, these transmissions can provide reliable service. Understanding the different versions, common issues, and proper repair procedures is essential for anyone working on these systems. Thank you for joining us in this comprehensive exploration of 6L80 TEHCM variations and failures. Armed with this knowledge, you're better equipped to diagnose, repair, and maintain these sophisticated transmission control systems.